Hello and welcome to the presentation of our themes technical paper. My name is Enes Yiğitbaş and I am a researcher at Paderborn University. Today I'm going to present our work on enhancing human-in-the-loop adaptive systems through digital twins and virtual reality interfaces. This is a joint work with my colleagues Kadiray Karakaya, Ivan Jovanovic and Gregor Engels. Let's start with the motivation of the problem. Usually, self-adaptation approaches rely on closed-loop controllers that avoid human intervention from adaptation. However, there are situations where human involvement is beneficial or even necessary. Human involvement is possible at different levels of the MAPK loop. For example, humans can act as a sophisticated sensor by incorporating information difficult to monitor or correcting the sensed anomalous value. Also, humans can incorporate input into the decision-making process to provide better insight about the best way of adapting the system. Furthermore, humans can act as system-level effectors to execute adaptations. Finally, on the knowledge augmentation level, users may provide personal input to personalize the systems and better fit their preferences by providing new knowledge. While human involvement is beneficial or even necessary, in some cases as mentioned already, the integration of the human in the MAPK loop brings various challenges that should be addressed both from self-adaptive systems and human-computer interaction perspective. We have identified the two main challenges, transparency and controllability. The first challenge in incorporating the human in the MAPK loop is supporting transparency. This means that humans need to understand what is going on in the autonomous system as well as its context. Providing the user with feedback, explanation, and visualization about the system state and its context is crucial to establish and keep the user's trust and spatial awareness. The second important challenge for human involvement in the MAPK loop is managing the degree and way of controllability. Concerning the degree of controllability, to ensure that the most suitable decisions are met, it is important that self-adaptive systems provide mechanisms to adjust the degree of user control. For instance, fully human-controlled or mixed initiative, depending on different circumstances. For example, changing goals, emergent behaviors, uncertainties, or simply that users prefer more control. Regarding the way of controllability, incorporating human input in the decision-making and adaptation process should be supported in a natural and interactive way. To better understand the mentioned challenges, let's have a look to a concrete example scenario which will be used throughout this presentation. In this scenario, we have a robot system that operates on an assembly line. The task of the robot is to put various objects together to build something. However, the position of the objects or the obstacles in the environment can dynamically change. As a consequence, the adaptation corresponds to changing the robot arm's motion trajectory. Depending on the safety criticality of the domain, varying degrees of human supervision can be required to intervene in these motions. For example, some assembly tasks may require more precise and sensitive movements, while some tasks can benefit from more autonomy. Thus, the question we are focusing on is the following. How can we support transparency and controllability for such self-adaptive systems? To answer this research question, our solution idea looks as depicted in this slide. To address the first challenge, namely transparency, the actual environment of the self-adaptive system is represented through a digital twin model in the virtual environment. This virtual environment can be accessed by the human through a virtual reality interface by using a VR head-mounted display. This VR interface supports intuitive, immersive, and remote control of the self-adaptive system, which in our case is the robotic system. With the help of the VR interface, we provide a natural and interactive way to increase the controllability and thus to tackle the second challenge. A more detailed view of the solution approach can be seen on this slide. Here, at the bottom, we can see the illustration of a Dobot Magician system that runs on ROS, on the robot operating system, and which characterizes the managed element in our case. For integrating the human in the loop, we have a VR interface for transparency and control that is shown at the top of the slide. The advantage of the VR interface compared to traditional graphical user interfaces is that the user can walk freely in this virtual environment and observe the robot and objects in the environment from different viewpoints. For this purpose, the managed element is monitored through ROS topics that publish visual data obtained by the Kinect camera, and through ROS services that return the robot's self-state. The monitoring information is used to reflect the digital twin of the system in a VR application for providing transparency to the user about the system state. To provide varying degrees of controllability, the VR interface offers a procedural control and a declarative control, which will be described in the next slides. The first control strategy that we implemented is called procedural control. With procedural control, the user can directly interact with the robot arm. The user can grab the ant effector, which is depicted with the green control sphere of the robot arm, to move it in the 3D space, and joints of the arm will be aligned accordingly. The user records the robot arm movements, which make up the exact motion trajectory for its ant effector, and sends it to the real robot for execution. In this short demo video, we can see the procedural control strategy in action. The second control strategy that we implemented is declarative control, a mixed initiative approach where the user only defines a goal state by moving cube objects. In declarative control, the user can grab the cube objects to define a goal state, and the robot figures out how to reach the goal state autonomously. To enable this, the system state, which corresponds to the configuration of the cube objects, needs to be extracted. For this purpose, each object's relation to other objects is calculated and represented as PDDL predicates. The extracted initial state and user-defined goal state are then combined to create a PDDL problem and sent to an AI planner, which returns a set of actions as the plan that leads from the initial state to the goal state. And here we can see the declarative control strategy in action. For evaluating our VR interface for human-in-the-loop adaptive systems, we conducted a usability evaluation with regard to effectiveness, efficiency, and user satisfaction. Based on these criteria, the main goal of the usability evaluation was to analyze and compare the advantages and disadvantages of both implemented human-in-the-loop control strategies, procedural and declarative control. We had 14 participants in our user experiment, and the task scenario consisted of 3 cubes with different colors and 3 target positions marked with the same 3 colors. The goal was to put each of the cubes to the target positions with the same color, using the VR interface in both control strategies. For evaluating the system's efficiency, we measured task completion durations by logging task start and end times. As shown on this slide, the average task completion time in the procedural control strategy is 172 seconds, and in the declarative control strategy, it is 112 seconds. In general, these efficiency results match the user feedback from the interviews, where the participants have frequently noted that they were able to complete the task in declarative control strategy faster. The effectiveness of the system was calculated for each of the control strategies as the number of successfully completed subtasks divided by the total number of subtasks. With regard to effectiveness, we can see that there are no differences between the procedural and declarative control of the VR interface. Nearly all of the participants, despite one, could successfully finish the given task. At this point, please note that we distinguish between the effectiveness of the VR interface and the managed element. Successful task completion in the VR interface doesn't indicate successful task completions by the managed element. The managed element's performance is affected by sensor data and in the monitoring phase. For example, the objects are not instantiated at their correct positions in VR. For evaluating user satisfaction, firstly, we asked the participants to fill out the system usability scale, shortly the SUS questionnaire. As a summary of the SUS questionnaire, we derived a SUS score of nearly 64 for the procedural control strategy, while the declarative control achieved a SUS score of nearly 81. According to the adjective scale, procedural control can be defined as between OK and good, which is in acceptability range, and declarative control can be defined as close to excellent. As a second step, we asked the participants a subset of a presence questionnaire, which is used for measuring users' feeling of being present in a virtual environment. We consider the user's degree of presence experience as a criterion for their satisfaction. As the way of providing presence doesn't change with the different control strategies, when asking the presence questionnaire, we do not distinguish between the two control strategies and cover the VR interface in general. With a presence percentage score of nearly 75%, we can observe that the user's feeling of presence is very good. To conclude this presentation, we have presented a solution to enhance human-in-the-loop adaptive systems through digital twins and VR interfaces. In this course, we have discussed the advantages and disadvantages of our VR interface for supporting transparency and controllability. As future work, we plan to improve our VR interface through multimodal input and output. Furthermore, we plan to extend and apply our solution for different types of human-in-the-loop self-adaptive systems in different application domains. Thank you very much for your attention.